Okay, let's get started with the next talk. We have Scott Smith on symbolic evaluation of functional languages.
Welcome to our talk on a higher order demand-driven symbolic evaluation. Let's parse this title a bit, particularly what is meant by demand-driven. Demand-driven means goal-directed. So rather than working forward, we're going to start with a goal and work backward. And this is well known from logic programming and tactic-based provers where it's clear what your goal is. And so it's best to start from that goal and work backward rather than trying to forward chain, although sometimes forward chaining is good. Generally, you're shooting in the dark a lot of times and you're very far away from your target. So goal-directed is clearly a win there, and it's the common approach. Now, if we look at program analyses, symbolic executors, and interpreters, it's more the opposite. There tends to be, you don't have a fixed narrow goal in the space. It tends to be you want to run the whole program in all of these cases, and so they tend to be forward. But there are some cases when demand is useful. If you have a particular part of the program you want to get a very accurate result on, a demand program analysis could be effective, and you don't have to go through all the work on the whole program. And so reps and collaborators wrote a series of influential papers doing this in the imperative language space, and there have been a few efforts in the functional space. One is DDPA, which is our work, so there have been some functional demand program analyses. And in the symbolic execution space, Snugglebug is an imperative demand symbolic executor. And this paper is basically about filling in this box with DDSE, which is our functional demand symbolic executor. And to do a functional demand symbolic executor, we need an interpreter, which is demand, in which we're going to symbolize. And so we're also going to present DDI, which is a new notion of functional interpreter, and it is novel and it has no substitution, environment, or closures, because you can't, these data structures are built in the forward direction and we're not running forward. And so the interpreter itself is pretty interesting. And so the outline of the talk is we're going to briefly talk about the language syntax, then we're going to do this novel interpreter, and then we're going to show how it can be generalized to a symbolic evaluator, and then we're going to look at our implementation very briefly. So the syntax we have is pretty standard, very simple functional language in our theory. And we're going to have input because the way we're going to test our symbolic evaluators, we're going to find inputs that reach a particular line of the program. That's sort of our concrete goal to show that the method works. And recursion is encoded via self-passing, and the implementation also has additional features such as recursive data structures. And the syntax we use is anormal form, and this is an example. And you can see in anormal form, every operator, the components are all atomic, and this exposes the order, which is very useful because we're going to be running programs backwards, so reading right to left, and it's very handy to know the order more explicitly. And also variable names unique, so here we have x, y, and ret, and those serve as the program points because they're unique. So we'll use that to name points in a program. So the main function we want to define is a lookup function. And the lookup function, we want to find the value of a variable. So that's the variable we want to look up. That's the point at which we want to start in the program to look it up. And this one parameter we'll talk more about is the call stack, which we use to disambiguate different activations. And the final result is a V. So this is the program point call stack. And this, in general, this is going to be a list, but for now we're just covering the case where it's a singleton. And the idea is we're just going to walk back through the program to find the variable, is the intuition. So here the variable y, if we're actually at its definition, it's axiomatic that the value is 1. But if we're down here at this line f1, so these don't remember the line we're looking up from the program point. So to find y, this y, we basically can search back up through it and we'll find it up here. And more interesting, if we're in, for example, this variable x here, the only way we're going to reach that is via a call from one of these call sites. And here, this disambiguates which call we took. So we were in the call f1 is how we got there. And we are pretty clear if we're looking up x from the call f1, x is the argument passed in as y, and then we can look up y and in turn get 1. So 1 is the result of that. So let's go through in detail how we trace that call, so a little more about how the actual lookup function works. And so to look up f1, at this point, we know that it's the return result of the function f. So it suffices to look up the return variable fret in that code at the last line of code, which is fret. So we're looking up from the point that we're pointing to, and we're looking up that variable. And the value is immediately there, just right in front of us. Oh, by the way, we have pushed a call frame because we're in this call. So f1 names the call frame that we're in on the call stack. And so it suffices for fret, clearly it's x plus 1. So all I get is look up x and add 1 to it, and we have our results. So we're going to look up x. That's the underlying lookup. So we're looking up x from the top of the function. At this point now it's pretty clear that since we came in via the call f1, we know that we came in this call here, and the parameter y is what gets passed to x. So to look up x, it suffices to look up y from the top of the program, the empty stack. And that pretty clearly is going to be 1, and then the final result is 1 plus 1, which is 2. So that's a simple lookup. And a little more complicated case is if you have non-local variables. And here's a simple example of a curried addition function. And let's start in the middle of this lookup. So we want to look up the value of x. And this is the tricky case because it's a non-local variable. It's defined all the way out here. And the way we got there, the way we're actually going to run this code, if you look at the program, it's going to be from this call site here. Because first we supply 5 for x and then 1 for y. And then we're going to do this call, in which case we'll run this code. So that means that we had to have come in via this call site, ret call site here. So this is an example of where we could have gotten to in a lookup from the end of the program, for example. And so we're at that line here, gyret, its definition. We want to find the value of x. So what do? Well, x is not in scope, but the principle of lexical scoping is the function we are running, i.e. this function here, gyret, we know that the x variable must have been in scope when that function was defined. As you can see, it's in scope at the function definition point. And so what we do is we know that that function is the value of g5 because that's the function we call. This is the call site we came from, ret, and that function g5 was called. So what we do is we write a lookup like this, which means let's first look for the function definition where g5's code is, and then pop that off and resume a lookup for x. And we should find it at that point. So let's do that. So to find g5, in fact, is the return result of this call. So we want to pop into g's body and look for gret, which will be the value of g5. So to look up g5, it suffices to look up gret from within this call at this line. So let's do that. And to define gret, well, it's right there. We found it. It's the last line of the code. So all we have to do now is to pop this frame off the stack and resume looking up for x. And look, we win. X is within scope now. So in fact, it should be very easy to find the value of x. It, in fact, is the parameter at the call site g5, which in fact is 5. So that's the answer. And so in general, the lookup, if we have higher and higher order functions, this list can grow longer and longer. But this is the full general signature of our lookup. So it has 2 lists of variables, basically, and that's all of the data structure of this interpreter. And here are the full rules. You can see it's a lot more complicated than the pure lambda calculus. So there are a lot of subtleties here, but it does fit on a slide, so it's not hopelessly complex. So let's now look at how we make a symbolic version of this. So it's a very similar parameters, and instead of returning a value, we return a variable, which, and then in the constraints, we also have a constraint set, and the idea is we're going to constrain that variable to have some properties, which we can then use an SMT solver to find an actual solution for. And so, yeah, so this S here means a symbolic version of lookup. So let's run that on the same example, the same lookup of f1's value. So we go into fret and look up fret's value, and we can immediately see it's right there. It's x plus 1. So we're actually, this time we're going to return a variable. And remember, the variables are indexed by the call stack. So this variable is indexed by f1 in this case, because that's how we came into this function. So that's in fact the result of the lookup. So we're done the result of looking up, but additionally we have a constraint which requires this variable to have the value of whatever x's lookup is plus 1. And remember, this lookup here is in turn going to return a variable. So let's proceed with that lookup and see what it returns. So to look up x from this point here, it suffices to look up the parameter of the call site. The call site was f1, so the parameter is y. So it suffices to look up y. And if we go up, we see y is up at the top of the program. It's in fact an input. So this is, by the way, use of the input syntax. And inputs are unconstrained because they could be arbitrary. And so in the symbolic execution, we just return the variable with no added constraints. So that means that the final constraint set is that this fret equals this lookup here, which returned just the value y in the empty stack plus 1. So we get that. That's the only constraint on this very simple example. And it's clear there are many satisfiable solutions to it. So that's an example of a symbolic execution. So in the paper, we make a formal operational semantics for all these systems. And the main result we prove, or the most difficult result, is that a backward running demand operational semantics, this lookup operation, is in fact isomorphic to a forward running operational semantics. And it's a delicate proof because they're running in opposite directions. And we also proved that the symbolic evaluator is sound and complete with respect to the operational semantics. And a few subtle details that we have to skip because of time is that the call stack, when we're starting in the middle, we really want to start in the middle because that's what demand lookup means. We want to start from any point. And you might not, you will have no idea of the call stack when you start that run. And we need to incrementally infer what the call stack is as we go. And also input will not come in the forward order when we're doing a reverse lookup, and we need to basically do a sorting operation on the input, and that's all in the paper. So for our implementation, the artifact we produce is a test generator. So given a program and a target line, we will find inputs which reach that target line of code. And we have an initial proof of concept implementation in OCaml, and in order to make it usable at all, we have to dovetail on all the different search paths or we get lost down some infinite path. And so we use a coroutine non-determinism monad for that purpose. And just to test it out a little bit, there is a paper that has a forward symbolic evaluator in it. And we basically solved the benchmarks from that paper just sort of as a test to make sure our system is reasonable. And to compare very briefly with related work, so Snugglebug is an imperative demand symbolic executor. The Cron's work that we just mentioned is a forward functional symbolic executor. And it also has restrictions. For example, all functions have to be total, which we don't have in our system. And Rosette is another forward symbolic execution framework. And it has some restrictions on data types not being arbitrarily sized. And our work has, it's the first that we know of demand functional symbolic evaluator, and it has no restrictions on data types or recursion, and we've proven it sound and complete. Thank you.
Thanks, Scott. In either time band, you should see a link appearing in Clouder to join a live Q&A session with at least one of the authors.